Hey everybody! So first things first, I know I sent an announcement to remind, but our last oh wow isn't going to be due this Thursday. I was looking at the material we have to cover, and I'm thinking you all don't want to watch a 2-hour video right now. So we definitely need 2 full days to get all of that material covered on that oh wow. So we'll get it done, the material done this Thursday, and then you can have the next week to get it done and hand it in. Our last oh wow, woohoo! So you have these packets. We were working on them last video, and I just made some notes for us as we'll kind of just plow through the rest of this section on fractions. We really won't even get it all done, but we'll get a little bit, a chunk of it done. So you should be able to get started on the oh wow, but we still have this also to cover, which is in Blackboard. So we've got a lot to do, so this will give you some time to do it. So looking at where we ended off, we were comparing fractions. And I know that I said that Engage New York has students refer to these benchmarks of 0, 1/2, and 1. So these ones are pretty obvious what the benchmarks are, right? These ones are pretty obvious. So the benchmark is 1/2. So let's think about, if my denominator is 4, what would 1/2 of 4 be? Okay, so obviously then this is bigger than 2/4. Okay, so here if we have 8, here I'll write over here. So if we have 8 in the denominator, then 1/2 would be 8 on the bottom, 4 on the top. So this is obviously 7/8 is going to be smaller than 1/2. So the mouth eats the 7/8. Right? I really wish I'd put this over here, 2/4 on this side, right? Because that's equal to 1/2. So 3/4 is obviously bigger than 2/4, and 7/8 is bigger than 4/8. Now this one is not going to be a benchmark to 1/2 because remember we have those rules. If the numerators are the same, we compare the denominators, and the larger the denominator, the smaller the fraction. So this one's going to be bigger. Now this, we're going to make some equivalent fractions out of because it's really easy to make that 5 into a 10. So if we multiply top and bottom by 2, 5 will become a 10. If we multiply 3 by 2, the equivalent fraction is 6/10. And then it's pretty easy for kids to see that if the denominators are the same, you're just comparing the numerators. All right. Now these ones are interesting ones. So these are both going to be using a benchmark of 1. Do you see these are both 1 piece away from having a full circle if we were looking at a circle being divided up into 3 parts? And a circle being divided up into 8 parts. Right? So this is 7/8 is 1 piece away from a whole. And this is, pretend these circles are the same size, 2/3. This is 1 piece away from the whole. It's a little exaggerated because I didn't draw the circles the same size, but I'm hoping that you can see that since these pieces are small, only missing 1 is going to make this really close to having a full circle. This piece is much bigger, the missing piece, so that this is further away from the 1. So we're using 1 as my benchmark. Now you can use that logic. You can either compare this to 1/2, right? We know 1/2 is bigger than 1/3 because of the denominators, or you can also say these are each 2 pieces from a whole. I can draw my circles better this time. Okay, so here's my 1/3, and only 1 piece is filled in. So there's 2 missing pieces. Here's my 2/4. So this is missing 2 pieces. Do you see that? And kids can easily see that the missing pieces are smaller. Therefore, when you're missing 2 to get to the whole, you're closer to the 1 with the smaller missing pieces. So there's a couple ways you could explain that problem. Okay? If we look at this one, we could use a benchmark of 1/2 if you wanted. This is equal to 1/2, right? This would be, and I think it's funny how they write this. So this is a half, so our benchmark is going to be half. I was looking in the notes, and so if they compared this to 1/2, the denominator being 3, they write it as 1 and 1/2. I think that's so funny to see in the solution manual. So we've got 2/3, and these are all different representations of 1/2. Do you see that? 1/2, 5/10, and 1 and 1/2 over 3. So obviously this one's going to be the one we're going to look at, and this is definitely smaller than that guy. So 2/3 is bigger than 1/2. Or you could have also done the missing piece concept, right? 1 missing piece here, 1 missing piece here. All right, benchmark of a half again. So this is bigger than 1/2. Does everyone see that this is smaller than 1/2? Bigger than 1/2, smaller than 1/2. So that's got to be bigger. Benchmark of a half again. This is smaller than 1/2. This is bigger than 1/2. Benchmark of a half again. This is bigger than 1/2, and that's smaller than 1/2, right? It would be 8/6 if that was equal to a half. So this is how they benchmark these. It's different, right? It's definitely a different way to think about it. I was always taught you convert it to decimals and compare the decimals, but that is not what is done. They're really getting them, these students in 4th grade, this nice number sense. Now these ones are good because it's getting kids to realize the difference between an improper fraction and a proper fraction. So if they're comparing 2 fractions, let's look at this one. So, actually, these are both improper. Okay, so let me show you what they're going to do. Here, we'll come back to this one. Let's take care of the other ones. So this is bigger than 1. This is less than 1. Improper versus proper, right? This is bigger than 1. This is less than 1. So improper is always bigger than proper. This is bigger than 1. This is less than 1. Proper, improper, right? Improper is always bigger than proper. You guys good with this one? This is proper, so it's smaller than 1. This is improper, so it's bigger than 1. All right, and then this, I think it would be pretty easy to make an equivalent fraction if we multiply both sides, or top and bottom, by 2. That'd be 14/10. So 14/10 is going to be less than 16/10. All right, so let's come back up and look at this one. I want to explain something. I'll probably wait to come down here. Let's just make maybe an equivalent fraction out of this, right? We can multiply top and bottom by 2. So this will be 14/10 compared to 11/10. So this side is going to be bigger. All right, so the new stuff that I thought was really interesting was this guy down here. But here, we'll do this one real quick. This, I think, is probably pretty easy to see that and explain. That's an improper versus a proper fraction. And 5/4 is bigger than 1. 7/8 is less than 1. So there's my benchmark of 1. So that's why 5/4 is bigger. And I like their directions. Use number bonds to help explain the second comparison. Okay. So these are both improper, and it's not a one-stepper to make these into fractions where the denominator is the same. So we're going to use these number bonds to explain it. So let's write this down as a mixed number. So this would be 4 over 4 and 3 over 4. So that would be 1. So this is 1 and 3/4, right? Okay. This is 5 over 5 plus 4 over 5. So this would be 1 and 4/5. All right, so now we're comparing 1 and 3/4 and 1 and 4/5. So the ones are equal, so we can take those out of the equation, and now we just need to compare 3/4 and 4/5. Now do you see these are both one piece away from a whole? Since these are smaller pieces, the one missing piece is small, so this number will be closer to the 1. Right? So using number bonds, we need only to compare 3/4 and 4/5. Each are missing one piece to get to a whole, or a value of 1. Since 1/5 is smaller than the missing piece of 1/4, 4/5 is closer to 1. It's interesting. Oops, sorry about that. Look at all that you missed. It's interesting. It's an interesting way to compare fractions. And they have them write them as improper fractions and get rid of the whole number part. And so now they're just comparing the proper fraction part. That's very, very different, but I really think it's interesting. And I think these kids in 4th grade and on will have a really strong hold of fractions, and they won't have like this kind of intimidation factor when they see fractions and word problems and operations with fractions. You know, we'll start covering that stuff in a little bit. So, in order to simplify fractions, in order to do multiplication and division and addition and subtraction, we need to understand greatest common factor and least common multiples. So there's a lot of applications to this stuff. So a fraction in simplest form is if the numerator and denominator are what are called relatively prime. So essentially, or I'll talk about let's talk about what relatively prime means. So relatively prime numbers are numbers that have no common factor other than 1. So for example, 3 and 5 are relatively prime because the only common factor they have is 1. So the fraction 3/5 would be what's called in simplest form. Okay? So we're going to use this to be able to understand how to get fractions in simplest form. It will all come together, I promise. All right, so let's talk about greatest common factor. So GCF means the greatest common factor. So there are a bunch of strategies in Engage New York, and I'm going to run through the 3 strategies that Engage New York walks us through. Okay, actually there's really 4 because they love their Venn diagrams as well. So strategy 1 for Engage New York, it says just list all the factors of these numbers. So factors of 45, well, 1 times 45 is 45. 2 won't go into it, but 3 times 15 will give us 45. 4 won't go into it. 5 times 9 will give us 45. 6 won't go into it, 7 won't go into it, 8 won't go into it, and you know you can stop when you hit the next, like if you're going in consecutive order and then you already have one, like if I said 9 would be next, you already have it listed, we've got them all covered. So let's look at 60, there's a ton. So 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, 6 times 10, 7 won't go into it, 8 won't go into it, 9 won't go into it, 10 does, but we already have it listed. So now I know I've listed them all. So what's common? The 1s are a common factor. Not 45, 3 are a common factor. 15 is a common factor. 5 is a common factor. So not 45, not 9. So these are all of the common factors. So you circle the largest one. So 15 is the greatest common factor. That's it. So that's the one strategy that they use in Engage New York. I'm going to show you it right here. I'm going to sneak over and I'll show you it. So this is out of Engage New York. I can't remember if this was 5th grade or 6th grade. I'm going to be on, I think it was 6th grade. But it says list the factor pairs, they call them factor pairs, to ensure that no common factors are missed. So find the greatest common factor of 12 and 18. All right, 12 is 1 times 12, 2 times 6, 3 times 4, and then we would end up with 4 times 3, so we have them all listed. Factors of 18 and 1, 18, 2 and 9, 3 and 6. We go not 4, not 5, 6, and we have 6 listed. So they said, circle all the factors that appear in both lists. So they circled 1, 2, 3, and 6. And they say place a triangle around the greatest of these common factors. So there's the triangle, and then 6 is the greatest common factor. All right? So that's an Engage New York strategy. You just list them, see which one is common. Look at this one right here. Says choose one of these problems that has not yet been solved. Solve it together on your student page. All right, here we go. So it says greatest common factors. So you list all the factors of 30, all the factors of 50. These are the ones they have in common, right? We could check them. They both have a 1, they both have a 2, they both have a 5, and they both have a 10. And then which one's the biggest? 10. So they're just having them list them out. But it gets cumbersome, right? Like 60 is a lot. I think it might be easy for kids to forget, like maybe 4 times 15. So it's a great method, but if the numbers are big and there's a ton of factors, I'm thinking they're going to maybe forget 1 or 2. But I don't know. That just seems like a lot to me. All right, let me keep going. Another very popular strategy is dealing with exponents, okay? And this is where kids are making these factor trees. So factor trees are cool. Most kids don't have a problem making factor trees. You just have to find any 2 numbers besides 1 in itself that you multiply together to give you 45. I think most people would think 5 and 9. And if any of them are prime, circle it. And then 9 is 3 times 3. Those are both prime, so we'll circle them. Okay, 60, I'm going to think of 6 and 10. Neither of those are prime. So we'll go 3 and 2. And then 10 is 2 times 5. So what they talk about in Engage New York, and I think pretty sure this is 6th grade, they have the kids write these out. Instead of 3 times 3 times 5, they have these kids write them out with exponents. That's why I'm sure that this is probably a 6th grade concept. Now, I personally, well, we'll talk, I personally like this because we can find the least common multiple pretty quickly with this as well. So it's a nice method because this will easily solve 2 in one shot for us. But so does the Venn diagram. So I like this method. So the greatest common factor says find all the factors that the numbers have in common. So what are the factors that they have in common? See, they both have a 3 and they both have a 5. And then they said take the factor with the smallest exponent. So if I'm looking at the 3, this is a 3 squared and a 1, so I'm going to keep it the 1. And these are both 5 to the first. So the greatest common factor is 15. So you write out the numbers with factor trees, write them out with exponents, take everything that's common with the smallest exponent that they each hold. Here, let's try another one, and so that'll clear it up. All right, we already did the factor tree for 45, but here I wanted to show you something. It doesn't really matter how you think of it. Maybe some people said, oh, I thought of it as 3 times 15. Is that going to make a difference? Nope, because at the end, we will have the exact same product of primes. Do you see that? So it doesn't matter how you start it. If, like if you said, if we come back here with the 60, and someone said, oh, I thought about it as 2 times 30, you would have gotten the exact same factor tree at the end. All right, 54, most people think of that as 6 times 9. And 9 is 3 times 3. All right, so let's write this out. So 45 is 3 squared times 5. And 54 is 3 cubed times 2. All right, so the greatest common factor. Here we go. So what you want to do is you want to find the factors that are common. So the only numbers that we have in common are the 3. And then you want the smallest exponent. So this has a 2, this has a 3, so we want 3 squared. So the greatest common factor, the largest number that will divide evenly into both of those numbers is 9. That's what a factor is. It's a number that will divide evenly into both of these numbers, and that's the biggest one that will go into both of those evenly. All right, so that's a nice strategy. I like this one because it's really easy to find the LCM with this as well. All right. Another strategy that I thought was kind of clever was, and this is an Engage New York strategy, it's also in our book, they said repeatedly divide by prime numbers. Okay. Until you can't divide anymore. So let's look at the 45. This is how they set it up. 45 and 60. So 2 won't go into these, but 3 will. So 3 divided by 3 goes into 45 15 times, and 3 will go into 60 20 times. And then they repeat it again. Is there a prime number I can get out of both of those that will divide in evenly? And you say, yep, 5 can. So 5 will go into 15 3 times, and 5 will go into 20 4 times. So it says repeatedly divide by prime numbers. Is there anything that will go into both 3 and 4? No. Nothing will go in besides 1. So then this column is your greatest common factor. So you're going to take 3 times 5. The product of that column, I should say, is your greatest common factor. That's different. I think that's cool. Here, we'll try it again. Ready? So we've got 45, and what was the other one? 54. All right. So we're going to go with repeatedly dividing by prime numbers. So 2 won't go into that, but the next prime number is 3. So 45 divided by 3 is 15. And then 3 will go into that. And it's just late right now, and I'm not going to do that, not even venture doing that in my head. 18. Okay, you got to repeatedly divide by prime numbers. So 2 won't go into those, but 3 will. So we've got 5 and 6. And you know you're done if you get 2 numbers that are what are called relatively prime to each other. Now look, I know that this isn't prime, but there's no number other than 1 that will go into both of them. So they're what are called relatively prime. And then this is going to be your greatest common factor. You take the product of that column. So that's kind of cool, right? That's kind of cool. So it says, when will the greatest common factor of 2 numbers ever be 1? When will the greatest common factor of 2 numbers ever be 1? Well, we just looked at these. The greatest common factor of 5 and 6. Well, let's look at the factors of 5, and then let's look at the factors of 6. Do you see the only common factor they have is 1? So if these numbers are what are called relatively prime to each other, their only common factor is 1, then the greatest common factor is 1. And when will the GCF be one of the numbers? Let me do this. So look, let me do the factors of 5. Factors of 5 are just 1 and 5. The factors of 10 are 1 and 10, and 2 and 5. So do you see that the greatest common factor of 2 numbers where 1 is a multiple of the other? That's when that smallest number is going to be your greatest common factor. Do you see that 5 is a multiple of 10? 5, 10. So if one of them is a multiple of the other, that number right there, that smallest number, is going to be your greatest common factor. Now, those you never have to regurgitate. I just thought they were interesting. All right. So we looked at these. We looked at these. Let's look at the LCM, and then we're going to look at another strategy that Engaged New York has, and it's the coolest strategy ever, and they use Venn diagrams to figure out the greatest common factor and the least common multiple. It's so cool. All right, here we go. So least common multiple, this is the very mathy definition of the least common multiple, but it's not that hard. Just think about what a multiple is, and you want the smallest. So let's list multiples of 8. So 8 times 1, 8 times 2, 8 times 3, 8 times 4. I'm just going to list a bunch. 8 times 5, 8 times 6, 8 times 7, 8 times 8, 8 times 9. Okay, that should give us enough, right? If we want to do 8 times 10, that will give us 80. Okay, multiples of 12. 12, 24, 36, 48, 60, 72, 84. All right, that should be enough. So it says, let's list the common multiples. So these are common. These are common. Right? Do you see all these common ones? Okay, so common multiples are 24, 48, 72, dot, dot, dot. So the least common one is 24. Does that make sense? Multiples? It's easy to mix them up. So here, let's look at what they've done. This is the 6th grade method. So they say list the multiples of 12. Here they're doing 18. List the multiples of 18. Circle the multiples that appear on both lists. And then put a box around the in common that's the smallest. The least common multiple. So, what can you say about the least common multiple of 18 and 40 before we attempt to solve it? So, I gave the most generic answer. It is a multiple of both numbers. What else? This is why we need to be in class together. What else can we say about it? Well, I know it has to be even. The number has to be even. Right? Because all the multiples of these numbers are even. And not only are they all even, but if we're talking about multiples that are going to be for this guy, does it make sense that the common multiple is going to have to end with a 0? Because all the multiples of this number are going to be ending in 0, like 40, 80, right? 120. So the number, the multiple, is going to end with a 0. That's cool. And what's the biggest number? I mean, there's an infinite number of multiples. But at some point, we know that we've hit the number, and any multiples above it are going to have to be too big. That you've exceeded the least multiple. Now look, 18 times 40 is 720. So I know the multiple will be 720 or less. That might be the least common multiple, but it can't be bigger than that. So the multiple will be either 720 or a number less than 720. All right, so let's find the greatest common factor and least common multiple using a strategy outlined here. All right, so let's go ahead and use prime factorization, that prime factorization tree again. All right, so 18 and 40. Take a pause, and however you want to calculate the factor tree, go for it. If you want to say 2 times 9, 3 times 6 for 18, it doesn't matter. You go for it. I'm going to do it. You do it. And we'll see if we get the same thing. Okay, take your time. Did we get the same thing? All right, so let's look. Let's look at 18. So 18 is equal to 2 times 3 squared. Does everyone agree with that? And 40 equals 2 cubed times 5. All right, the greatest common factor. That's what we were doing before. So we wrote down what was common. The only one they have in common is a 3. No, sorry, is a 2. And the lowest exponent for the greatest common factor is a 1. So the greatest common factor is a pretty small number. It's only 2. 2 is the only factor that these guys have in common. All right, the least common multiple. So I always think of this as the LCM, LCM, LCM method. So if we were going to Peaches and Cream, if it were open, we would want the most flavors that we could get. So the flavors are the different numbers. So we would want the most flavors. We want a 2, we want a 3, and we want a 5. Those are the flavors of our scoops, and we want the most scoops that we can get. So we're going to take the highest exponent of each. So the highest exponent of 2 is a 3. The highest exponent that 3 holds is a 2. And the highest exponent that 5 holds is a 1. So let's pop that into our calculator and see what we get. Did you guys get 360? So I call that the LCM method. It's going to Peaches and Cream, getting some ice cream. I want all the flavors that I have, all the different numbers that are represented with the most scoops, and that's my exponent. So it says when finding the LCM, take the larger exponent of all the factors in either number. The old LCM method. So that's strategy 2. Okay, that's an interesting strategy. I like that one because you just make a factor tree and you knock it off. But let's look. Oh, let's do one more example, and then we'll do Engage New York. All right, so LCM. So pause the video. Just pause. Give it a pause and find the LCM of those, okay? All right, so let's see. So we had that before. So 40 equals 2 cubed times 5. That's not a shocker. 72 is 9 times 8. That's 3 times 3. And then 2 times 2. Okay, so 72 is 2 to the third times 3 squared. All right, so I always line them up. So we've got 2 cubed times 5, and 72 is 2 cubed times 3 squared. All right, here we go. You're ready. So the LCM, the old LCM method, it's like ice cream. We want one of every flavor. So I want a 2, I want a 3, and I want a 5. The highest exponent that 2 holds is a 3. The highest exponent that 3 holds is a 2, and then we've got our 5 to the first. So 2 cubed times 3 squared times 5. There we go. There's our 360. That's weird. We just did one. That's weird. They have 360 again. Least common multiple. So if we had to list all the multiples of 40 and all the multiples of 72, the first one that we would hit in common is 360. All right. Let's check out Engage New York. They use Venn diagrams as the coolest thing ever to figure out GCF and LCM. All right, so let's look at this. So it says, so I don't know, let me try to zoom in. I can't zoom in on this. Once you start recording, and I forgot to turn the lamp on, but it looks, I don't know if that's too bright. I don't know, maybe it's a little too bright. I can't tell. I don't know. Okay, so hopefully you guys can see better than I can, but they made their little tree diagram. So 30 is 2 times 3 times 5, okay, and then 50 they said is 2 times 25 and then 5 times 5. Okay, I've got to write that bigger because my old lady eyes can't see that. So 30 is 2 times 3 times 5, and 50 is 2 times 5 times 5. Okay, so they made these two Venn diagrams. But pretend I'm making it. All right, so these are the factors of 30, and these are the factors of 50. So the intersection is what they have in common. So they each have a 2 and they each have a 5 in common. So for the 30, do you see they're going to put the 3 on the outside that's not common with 50. So now we've got the 30 taken care of. So 30 is 3 times 2 times 5. Yep. And then the only factor we haven't considered for 50 is the 5. So 50 is 2 times 5 times 5. So the greatest common factor is the intersection. The greatest common factor is going to be the intersection of these two numbers, or the intersection of these two sets. So it'll be 2 times 5. The greatest common factor is 10. Oh, wait for it. It even gets cooler. The LCM is going to be the union of everything. So 3 times 2 times 5 times 5. No joke. It's the coolest thing. 3 times 2 times 5 times 5. 150. So the LCM, the greatest common multiple, is 150. It's so cool. So here, let's write this down so you guys don't forget. So how can you determine the GCF using Venn diagrams? The GCF of I'll just say sets A and B is the intersection of A and B. So if we're looking at 30 and 45 up here, or holy snap, 96 and 144, wowza, look at those trees. So if it's all organized for us, the greatest common factor is going to be 2 times 2 times 2 times 2 times 3. So the greatest common factor is going to be 2 to the 4th times 3, and the LCM is going to be 2 times 2 times 2 times 2 times 2 times 3 times 3. So 1, 2, 3, 4, 5. 2 to the 5th times 3 squared. You want to take the product of all the numbers that are in there. That's kind of cool. So 2 to the 4th times 3 is the one factor that will divide, the biggest factor that will divide evenly into both of those numbers. See, look, let me show you what I mean. So 96 divided by 48 goes in evenly. 144 divided by 48 goes in evenly. So this is the biggest factor that goes into both. The least common multiple, 2 to the 5th times 3 squared, is 288. So if we started listing out the multiples of 96 and 144, the first one that they would have in common, the first one that they would hit, the smallest one, is 288. And it's all done with Venn diagrams. I think it's so cool. All right, so how can you determine the LCM using Venn diagrams? The LCM of sets A and B, I'm just calling these two sets, okay, is the union. Is the union. And let me tell you, you could have, they could ask you to find the least common multiple of 3 numbers or the greatest common factor of 3 numbers, and it would be the same thing. You could make Venn diagrams with it, or you could use the Lickham method. It doesn't matter if they have 2 numbers, 3 numbers, 5 numbers. It's still the same concept. It's so hey, so oh wow. The very last question, I hated the way I worded it, so I changed the wording today, which is Monday. So if you haven't looked at it, perfect. If you've looked at it and you're like, I don't know, I don't have a clue what she meant, don't reprint it. Just look at the directions again. I asked you to make a Venn diagram using the factors, and it should have been make a Venn diagram using the prime factorization of the two numbers to figure out the LCM. So for that problem, you just want to use the union of the prime factorization that you're going to make of those numbers on the OWOW. But I changed the directions. But here, let's finish this off. All right, let's finish this off, and this is kind of how you want to mess with your oh wow. Right, so we'll do this question, and then I'm going to ask you one more question, and then we'll call it a day. Or maybe I'll start the video. So here, we'll do it right, we'll stop it right here. Okay, we'll stop it here, and this is where we'll pick up on Thursday. All right, so prime factorization of 18. Prime factorization means your factor trees. Okay, so this is going to be 2 times, I'll just do it that way, 2 times 3 times 3. I guess that's the best way to write it. And then 40, we'll have 4 and 10, 2 and 2, and 2 and 5. So 2 times 2 times 2 times 5. There we go. That's what those are going to look like. So if you're asked to place these on a Venn diagram, one set, I'll just write a little 18 out here, so that will remind us that that's my factors of 18 that have to fit in that set. And this, I'll write 40 to remind me that the factors that are going to be in that set have to multiply together to give me 40. Okay, so what do they have in common? Well, they each have a 2 in common. So that's going to go inside. All right, then for the 18, we have to have a 3 and a 3. And then for the 40, we have to have another 2, another 2, and a 5. So the greatest common factor is the union. I'm sorry, is the intersection. The greatest common factor is the 2, and I'll just put inside here the intersection. Okay. The least common multiple is the product of all the numbers. 3 times 3 times 2 times 2 times 2 times 5. Let's just pull out our calculator. 3 times 3 times 2 times 2 times 2 times 5. Boy, a 360. Again, a 360. I think we did this one already, but now we've checked it again using Venn diagrams. It's cool. So this is why I was a little overzealous thinking we were going to get this done. We need a whole nother day to get the stuff done on the oh wow. So on Thursday we'll finish this, and then we'll work on this, and then we'll finally be done with the material on the oh wow. I'm sorry about that. So anyway, we'll talk to you guys on Thursday. I hope everything is well, and I hope you're all healthy and happy. And if you have any questions, feel free to Zoom. Okay, we'll talk to you soon.